All right, we are live. I'm just going to send this link out. If you're watching on the replay, you can fast forward a little bit. And we'll get started in a minute. Okay. I'm apologizing in advance for all the clicking that you're hearing. And probably how close my head is to the camera. Okay. So we are live. We are talking about Unit 1. I'm going to give everyone a minute or two to get on, and we will go from there. Oh, Harper's barking. I'm going to go get Harper. When I get back, we will start. Harper, come here. Harper, do you want to eat? Hey, come here. Want to eat? Come on. All right, if you guys just jumped on, I was just letting the dog in. And we're going to give everybody about another 30 seconds to get on here, get ready to go, and then we will do the review. We're going to work through some of the questions on the review sheet. Otherwise, you can ask questions at any time if you have them, and that's kind of our plan. If you have questions, what I would love for you guys to do is either put them in the YouTube chat box, which is just, you have to be logged into your account, or just send them to me on Remind. Either way works. But again, we'll give everybody about 30 more seconds, and then we'll get started. Okay, so it looks like our numbers of people jumping on have stopped. So here's the deal with a live stream. I'm going to go through kind of a mix of questions, things that I think are important or that we've been struggling on. And then from there, if you guys have questions, send them to me at any time. You're on a little bit of a delay from me, so I will sort of pause, give you guys a second to digest things. And you can send questions either on Remind or on the YouTube chat box, which is on your screen. So starting with the first big topic, which is any sort of simplifying or solving, right? That's kind of where I want to start. So let's start with some factoring practice. Now, I expect that we can look at a lot of factoring problems and, go through them pretty routinely. We've factored a lot in our years past, but there are some that I want to focus on. So one of the things I've been seeing us struggle with in class is trying to factor problems where we have a leading coefficient but no GCF. So make sure if you have a case like this where you have a leading coefficient that's not 1, but there's not a GCF where you can just factor it out, then we're going to have to use AC factoring, right? So here I'm saying, okay, these two things multiply to be negative 26. And then I need two things that multiply to be negative 26 that add up to be my middle term. So in this case, 26, my factors are 1 and 26 or 2 and 13. And so if I did 13 and negative 2, that would add up to be positive 11. Now, we need to be careful because that's not my final answer. What I need to do with that then is split up the middle term. So the first term is going to stay as it is. The last term is going to stay as it is. But that middle term I can break up to be 13x minus 2x. And notice if we recombine those that we would get back to 11x, right? So now we're going to factor by grouping. So group your first two, take out an x. That leaves you with 2x plus 13. Second two, take out a negative 1. That leaves you with 2x plus 13. I know I've done it right because these two match. And because they match, that means that they're common. So I can take out 2x plus 13, and that leaves me with just x minus 1. So again, that's something you might need to do. You might not just get that problem on its own, but you will need to be able to factor that when the problem gets a little bit more difficult. Okay, let's go to the next one. And again, at any time, if you have questions, let me know. So here's the next one, factoring with fractional or negative exponents. When you're factoring out a greatest common factor, remember that your greatest common factor should always be your lowest exponent of that term. So in this case, I've got x to the 4/3, x to the 1/3, and x to the negative 2/3. All of those have the same base, but this is my lowest exponent. So that's what I'm going to factor out. So I'm going to factor out an x to the negative 2/3. Now I'm looking at the numbers. That's a 3, that's an 18, but the leading coefficient's a 1, so there's not also a GCF there. So I take out my x to the negative 2/3. So let's look at what's left. So I know that this would be an x. And when I'm trying to factor out, remember what we're doing is we're trying to subtract out the negative 2/3 because we're dividing that out. So if I do 4/3 minus negative 2/3, remember that would be the same as addition. That's 6/3, which would be squared, minus 3. Now here I'm doing 1/3 minus negative 2/3, which is to the first. And here you're factoring out the negative 2/3, which is what you're already starting with. So that would be minus 18. Now I would then always ask yourself, can I factor further? So here, this is x to the negative 2/3, and then x minus 6 and x plus 3. If it says to factor, you can stop there. If it said to factor and then rewrite with positive exponents, you would want to rewrite this. So you'd actually have x minus 6, x plus 3, and then it could be all over x to the 2/3. Notice it didn't ask me to solve, so I am not actually getting an x equals, right? I'm stopping in its factored form. Okay, so continuing on, number 3 is just laws of exponents. We've been doing pretty well, 4. We've been doing pretty well on that, but if you have questions, send them. Number 5, again, is just factoring out your lowest common exponent. Here, if that's x to the 1/2 and that's x to the negative 1/2, that's what I would factor out, right? Take out that x to the negative 1/2. So let's actually go through this one because this one gets a little more complicated. So 1 plus x squared, the lowest exponent of that is negative 1/2. And they don't have anything else in common. This one has an x squared, but the other one doesn't. So I am going to see what's left over. On this first one, I'm taking out a negative x squared. So if I do 1/2 minus negative x squared, that leaves me with 1 plus x squared to the first, minus, on this one, you're taking out that to the negative 1/2, and so that just leaves me with x squared. And this is all over 1 plus x squared. And now let's see if we can go any further here. So in this bracket, I can combine these x squared minus x squared. So that actually just winds up becoming a 1, right? And so this is just 1 plus x squared to the negative 1/2 all over 1 plus x squared. And that's all well and good, but those have a common base, so I can actually combine those more. If I subtract my exponents, that's the same as 1 plus x squared to the negative 3/2, because remember this is all to the first. And that would be equivalent to 1 over 1 plus x squared to the 3/2. So that's where I'm getting that totally simplified form. Again, if you have questions as I'm going, send them along. I see that you're with me. Just send questions if you have them. Okay, for the next one, it asks me to rationalize the numerator. And remember, rationalize means we want to get rid of anything irrational. And in our case, that means the radicals. So, rationalizing the numerator, I'm going to need to multiply by the conjugate here. The conjugate is when you keep your first and second terms, but we just change that middle term. So here, I'm going to leave this. My conjugate is going to be square root of x plus 3 plus radical 5. And in a fraction, whatever I do to the numerator, I also need to do to the denominator. So I am adding those on the denominator as well. So now taking this, I'm going to multiply through. In my denominator, I'm actually going to keep that in its factored form because it's going to save me some time, because hopefully something will cancel out, right? Nothing's going to cancel right now, but hopefully something will in the long run. In my numerator, I'm actually going to multiply these out. So this times itself is x plus 3. With conjugates, your two middle terms will cancel out. That's the joy of a conjugate. And then minus 5. So that's what I get when I actually multiply those out. Now I can simplify that more. That makes my numerator x minus 2. And this would be x, whoops, no, I do not want to sign into iTunes. X minus 2 over x plus 3 plus radical 5. And then we can do a little canceling. So the x minus 2's will cancel. So that's going to give me 1 over the square root of x plus 3 plus radical 5. Notice here that my numerator is now rational, right? It is just 1. My denominator is now the irrational part. So my denominator, or my numerator, is rationalized. All right, and then the last thing I want to talk about with these is solving and stating any restrictions. So noticing when something is actually going to be undefined. So for this one, I want to solve for x, stating any restrictions. So again, we're looking at a GCF here. So looking at these three, my lowest is the third term, the negative 4/9. So I'm going to take out x to the negative 4/9. But I also see that each of these have something that's divisible by 3. So I'm also going to factor out a 3. And then let's see what's left over. So the 3 would be gone. We factored it out, right? And then this would be 14/9 minus negative 4/9 is 18/9, which is 2. Minus 4, because we're doing 12 divided by 3. And then 5/9 minus negative 4/9 is 1/9, so, or 9/9, which is 1. And then minus, we're taking out the negative 4/9, and 15 divided by 3 is 5. So that's where I get to. Now we can factor that more. So 3x to the negative 4/9. This will give me x minus 5 and x plus 1. And then once we have it in factored form, if they multiply to be 0, each thing could equal 0. So x plus 1 could equal 0. That gives me x equals negative 1. X minus 5 could equal 0, which gives me x equals 5. And then 3x to the negative 4/9 could equal 0. But actually, if we think about that, that's 3 over x to the 4/9, right? You can never have 3 over a number and get out 0. It's not a thing that can happen. So this actually can't equal 0. And that would be undefined whenever x equals 0. So that is my exclusion. So I've got 2 solutions and 1 exclusion, right? Okay, we're going to move on. If you still have questions about this, the answers are all up on OneNote, but I am happy to answer them. Just shoot me a text. All right, let's talk about transformations. And again, if you have questions, just send them my way. So transformations, remember we're talking about horizontal translations being inside, vertical translations being outside, right? Your horizontal ones are always sort of the opposite of what you think. Your vertical ones are always directly what you think. We're not going to do many of these. I actually think we're pretty strong at these, but let's make sure we're okay. So give a function f, or given f, which of the following represents a horizontal stretch, that tells me it's going to be inside, by a factor of 3. Now, if it's stretching by a factor of 3, then what that tells me is I should actually be multiplying by 1/3, right? By the reciprocal of that. So it needs to be inside, which this is multiplying outside, this is multiplying outside. That's adding, not that. And if it's inside, it should be the opposite of what we think it should be. That should be the 1/3. So that would be B. Now, an interesting one that a lot of people I think will miss would be number 3. So number 3 says, given a function f, which of the following, 4. Given a function f, which of the following represents a vertical shift 4, followed by a reflection across the x-axis. And this is where order kind of matters. So a vertical shift of 4 would be f of x plus 4, right? It needs to be on the outside. But the thing that we need to remember, and actually you can eliminate some of these inside functions from there, is it says we're then taking that function and flipping the whole thing, right? So a lot of people will be like, oh, just make the first part negative. But we're flipping this entire function. So I actually need to make the entire thing negative, right? And so what I wind up there is negative f of x minus 4. And graphically, let's see why that makes sense. I'm just going to zoom in over here so we have a little bit more space to write. So graphically, think about this. If you move up 4, you'd be about there, right? But then if you reflect over the x-axis, it's akin to you having moved down 4 because we're reflecting over the x-axis there. So that is why that flips. And you can always sort of check yourself that way, draw yourself a picture. But a lot of people here would have put B because they didn't think about the order that they happened in. Okay, let's go to our next part, which is polynomials. And again, if you have questions, please send them to me as we are going through this. I'm here for you guys right now. All right, so next one, without the use of a calculator, which you won't have, so don't get used to it, we're going to use this function for each of the questions below. So the first thing it says is describe the end behavior, right? So on the end behavior, I'm looking at the degree, which is the highest exponent when it's written in standard form. And I'm also looking at the leading coefficient. Is it positive or negative? And so let's take a look at this one. So this is already in standard form, which is very nice for me. The degree is my highest exponent, so that's x to the 5th. That's odd. So odd should make you think, okay, an odd end behavior will be like a line. It will either be like a line with a positive slope or like a line with a negative slope. It will be where your end behaviors don't match, right? Then I need to know what my leading coefficient is. Here it's a 1, which is nice. That's positive. So that tells me that I have a positive leading coefficient. And so it will be like a line with a positive slope. It will go down on the left, up on the right. So what I know then is that as x approaches infinity, that's the right side, p of x should approach infinity. That's going up. As x approaches negative infinity, p of x should approach negative infinity. That's going down. Because on the left, it's going down, and on the right, it's going up. All right, now we can kind of fill that in on our picture if we want to. We can remember that this will go down here and up over there. And look, it looks like a line with a positive slope. All right, find the roots. The roots are going to be the values that make the function equal 0. So we're going to set this function equal to 0. So I've got 0 equals x to the 5th, blah, 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 blah. I'm actually going to start factoring. I'm not going to recopy the whole thing. So first thing I see is that there's a greatest common factor. So I'm taking out an x squared, x cubed minus 5x squared minus 4x plus 20, right? And from there I can keep factoring. So I've got x squared. This is factoring by grouping. So taking out my GCF of the first two, that's x squared. Second two, that's negative 4. And in each case, that leaves me with x minus 5. I know I just did that a little bit fast. And then last, I can factor that x squared minus 4. So that's going to be x minus 2, x plus 2, and I still have x minus 5. And double check yourself. We know that this is x to the 5th. Is this still a 5th degree? Do we still have 5 roots? So I've got 1, 2, 3, and that has a multiplicity of 2, so that's 4, 5. So my zeros here are x equals 5, negative 2, 2, and 0, and that one has a multiplicity of 2. The rest have a multiplicity of 1. So I'm going to start sketching this on the graph. So at negative 2, at 0, at 2, and at 5. I know it will hit 0 there. All right, now intervals of positive and negative behavior. I know some of you guys can just sketch on the graph, but I would like you to really be doing this algebraically and thinking about your, positive and negative factors, because that's going to matter. So here, I've got 4 zeros. So I've got negative 2, 0, 2, and 5. And we're going to start by looking at the number of positive or negative factors in each term. Now, again, if you say, oh, I know that the end behavior here is down, you could confirm that, in fact, over here it would be down, right? It would be negative. So looking at that, let's say we plug in -3. This would be positive because it's squared, negative, negative, and negative. So 3 negative factors, that will give you a negative. And then plugging in here, we can tell this will be positive. You could plug in the numbers, right? Or you could think about the fact that we know it has to cross here because it has a multiplicity of 1. All right, and at 0, we could plug in again, but also at 0, we know we have a multiplicity of 2, so it should not cross. And then again, you could continue from there, either plugging in or checking your multiplicities. So for my sketch, and again, I haven't finished this yet, but we know it's going to be cross, tangent, cross, cross, right? It should just touch there. So to actually answer this, you actually need to give me the intervals, right? So the intervals where it's positive are going, excuse me, there were 3 of them, going to be from -2 to 0, from 0 to 2, and from 5 to infinity, right? We've got 3 intervals. The reason that I don't list -2 all the way to 2 is that at 0, it actually equals 0, right? And so we don't want to list that whole interval because there is a point in there where the function is not positive. And then for our negatives, we have from -infinity to -2, anywhere it's below the x-axis, and from 2 to 5. All right, cool. So that is the bulk of what you need to know with polynomials. And I just closed out that program. Let's reopen that. Okay, cool. Let's talk rationals for a second. Let's talk rationals. You really need to know how to identify these different features, right? So I'm going to go through a few of them. I'm not going to go through all, but I want to leave some for you to practice with. So let's start by looking at number 2. So I want to know here where is my horizontal asymptote, vertical asymptote, and holes, or infinite discontinuities and removable discontinuities. So let's start with horizontal asymptote because we don't actually need to do any work for that. What you're going to do here is look at your dominant terms, right? So in each case there, it's the one with the highest degree. Those have the same dominant term or same degree. And so I'm going to divide the leading coefficients, which would be 2. For the infinite discontinuity and the removable discontinuity, we have to factor if possible and then go from there because we're going to look at what makes those factors equal 0. So this is not factorable. The numerator and denominator are already completely factored. So I see that nothing cancels out, so I know there will be no removable discontinuities. However, there is a 0 in the denominator still. So for the infinite discontinuity, I'm going to look at what makes the bottom equal 0. Here that will be x equals -1, and so that is my infinite discontinuity. And we'll talk a little bit more about those in a second. Let's do one more where we might have a removable discontinuity because if I look at this, I actually see that this is factorable. So I'm going to factor this. So this is x minus 1 in the denominator. In the numerator, it's going to be 3x minus 2, x minus 1. Again, you could do AC factoring there. You could use guess and check, whatever works for you. But I do see that I have a factor that will cancel. So let's start with the horizontal asymptote. The horizontal asymptote of this, look at your dominant terms. That's dominant in the numerator. That's dominant in the denominator. The numerator is growing faster. And so because the numerator is growing faster, I would say this has no horizontal asymptote. There is not one. It's just going to keep growing forever. For the removable discontinuities, let's see what we can remove. So removing from the equation, the x minus 1's cancel, right? So that means my removable will be at x equals 1. And then to figure out the y value, we're going to plug back into whatever's left over. Because this is really what's left over as long as x doesn't equal 1, right? So plugging 1 into that, I get 3 minus 2, which is, or 3, I'm sorry, that's a 1. No, that's a 2. Yeah, so that should be a 2. And then for infinite discontinuities, we're going to look at anything that's left in the denominator. Spoiler alert, the only thing left down there is a 1, so there are none. So make sure that those are rules that you know what goes with each, okay? And then the last big thing with rationals is figuring out the behavior near the infinite discontinuities. That is to say, we know that there will be an infinite discontinuity, or in other words, a vertical asymptote, at some value. And I want to know, is it going up? Is it going down? Sort of what's happening around it, right? So let's start with this one. I'm going to figure out where the infinite discontinuity is, which here would be at x equals 3. And so then I want to know on either side of 3 what's happening, right? So I start by looking at a number line. And I am looking really, really close to 3. I want to be like infinitely close to 3 without actually hitting it. So let's say I'm just to the left of 3. That would be where x equals maybe 2.99. If I plug that into this function, what's going to happen? Well, 1 will always be positive. That's my numerator. And the denominator is an absolute value. So even though 2.99 minus 3 would be negative, when you take the absolute value of it, it will be positive, right? So this will actually approach a positive number from the left. So what I would say there is, as x approaches 3 from the left, y approaches positive infinity. And I'm using y because that's the way my function is defined. But if it was a p of x or an f of x, that's what you'd want to say. You want those to agree. Now, if I go just to the right, let's say that's 3.001, whatever you want it to be. Same thing, numerator is just 1, denominator is an absolute value. So I could say as x approaches 3 from the right, y also approaches infinity. And so for the graph, it would mean we're approaching infinity from both sides. All right, let's talk logs. Let's make sure we can convert and condense and expand. And then we're going to get into trig. So let's start with evaluating. So with evaluating, I want you to remember that logs are, say it, I hope you said exponents, right? Logs are exponents. So if I'm evaluating, that's what I'm asking you. I'm saying what power of 16 equals 4? Or in other words, 16 to what power is 4, right? That's where the converting thing comes from. So, well, the square root of 16 is 4. So this would actually equal 1/2. Remember that if there's no base written, your base is 10. If it's an ln, your base is e. All right, let's convert one or two of these. So let's actually start with b. So I've got exponential form here. Notice that my base is 4, my exponent is 3, and that's the answer. So again, people have ways of remembering this, Ben, Bone, Benny, whatever. But here, remember it's a log. So I was like, okay, what's the base? Bases go in the basement, so base 4. Logs are exponents. It should equal the exponent. And then the answer is 64. And then say it back to yourself. Does this make sense? What power of 4 is 64? That power is 3, right? Okay, one other one of those. So here I've got ln 2x plus 1 equals 5. Looks a little scary, but remember with ln, your base is just e. So this is saying what power of e equals 2x plus 1, and that power is 5, right? So e to the 5th power equals 2x plus 1. Okay. Again, continue to send questions as you guys have them. I'm going to do one expand, one condense, and then we will trig it up, and then we'll be done. Okay, so let's do, let's look at number 5. Or B, sorry, not number 5. So on B, I see a couple different laws of logs. Remember, we've got when we add logs, we can multiply what's inside. When we divide logs, we can subtract. And when we raise a power to a power, we can multiply it out front. So here, this is out front. That means it was originally a power to a power, right? So this is log of x to the 5th. This is log of y to the 4th. And then I am adding, so I can multiply what's inside. So this would be log of x to the 5th, y to the 4th. Remember, we can go the other way. So conversely, let's say I have one like this. So I see log base 8. That's great. That means all my logs will have base 8. And let's see what we know. So this is multiplication. This is division and then an exponent. So this will be log base 8 of 8 plus log base 8 of A, because those are being multiplied, minus the 3 can come down because that's an exponent, log base 8 of B. And something that you may see is, log base 8 of 8, I know what that equals. So you may actually see, like, let's say it was a multiple choice, an answer where that was actually just a 1. Because 8 to the first is 8. All right, trig, everybody's favorite. Let's look at a couple of these. So first of all, you got to be able to find exact trig values, whether it is secant, cosecant, sine, cosine, tangent, cotangent, any of them. Positive angles, negative angles, and you will not see a degree on this test. You will only see radians. So make sure that you're comfortable with those. If at this phase you're still needing to convert between radians and degrees, then I would say that's fine. But as we move forward, pick a time to come see me so we can get more comfortable with radians. So looking at these, remember the difference between quadrantal angles and then angles that are within the quadrants. So for instance, if I ask you for sine of pi over 2, that's actually quadrantal. That's between quadrant 1 and 2. With quadrantal angles, you're going to think about the coordinate there. So that coordinate is 0, 1. Sine is your y value, so that would be 1. Okay, let's say I ask you for cosine of 11 pi over 6, right? So first of all, let's identify what quadrant we're in. 12 pi over 6 would be 2 pi, so this is just short of 2 pi, right? We're in the fourth quadrant. In the fourth quadrant, all students take calculus. This is going to be a positive answer, so I know I'm positive. And my reference angle is pi over 6. So you should be making that chart as soon as you get into the test. And the cosine of pi over 6 is radical 3 over 2. Tangent is very similar, 5 pi over 4, consider your quadrant. Let's flip to a more interesting one. So let's try, how about secant of 5 pi over 6? Let's do that middle one. So for this one, secant, remember you are actually going to find the cosine, and then you're going to flip it, right? So let's start with 5 pi over 6. What quadrant are we in here? Here, we are just short of 6 over 6, which would be 1 pi. So we're actually in quadrant 2. In that quadrant, cosine is negative. So now I need to figure out my cosine there. My reference angle is pi over 6, and we already said cosine of pi over 6 was radical 3 over 2. So that right there is the cosine of 5 pi over 6. We want the secant, so we're going to need to flip it. So I know that this will be negative 2 over radical 3, which is all well and good, except that you probably want your answer rationalized. So multiply the numerator and denominator by radical 3, negative 2 radical 3 over 3. And again, I'm going to leave some of these for you guys to work on individually, but if you have questions, send them. You guys are very quiet. I know it's Saturday afternoon, but... All right, these identities, while I'm waiting to see if there are questions, you need memorized, every single one of these. There are 11 that you need to know. Remember that I would say if you know this one, you can figure out the other two by doing division. So if you don't have those memorized, it's not the end of the world, but it really will be helpful if you know them. Anytime you see a 1 and a squared, look for that, okay? You guys have done pretty well on these, and I actually can post more links to videos if you want them. I have a ton more going over these. I'm just going to pick a couple that I think are a little trickier or just things you might want to take a look at, and then we'll do an equation or two. So starting and looking at number 2, a lot of people will see this and like freak out because they just don't know where to start. And what I would say is this is where knowing your Pythagorean identities help. I see a 1, I see a squared, I'm going to sub in what I can. So 1 minus cos squared is the same as sine squared. And secant squared minus 1 is the same as tangent squared. So now at least I can get everything in terms of sine and cosine and I have somewhere to go. Otherwise, you're going to have common denominators and all this other stuff that's just going to make it really hard. So let's see what we can do. So I can make this sine squared. Tangent, I can make it sine squared over cos squared. And then I can do keep, change, flip. So that's going to be sine squared times cos squared over sine squared. And through some magic of division, that winds up giving me that cos squared equals cos squared. All right, the other one that I wanted to look at was number 6, because this one, there's not a whole lot you can do to start. So looking at number 6, not a whole lot you can do to get started. Everything's already in terms of sine and cosine. I mean, your best bet might be making this 1 over cos, right? But still, you're like, okay, what do I do with that? So on the left side, if you want to combine these, the only option you have is to get a common denominator. It's all you can do. So I'm going to multiply this side by cosine, this side by 1 plus sine. And what that gives me is 1 plus sine squared plus cos squared over cos times 1 plus sine. Okay, add your numerators when you add fractions. Now, 1 plus sine squared, I can expand that out. That's 1 plus 2 sine theta plus sine squared theta plus cos squared. And my thetas are not connecting for some reason right now. All over cos times 1 plus sine. And here's the magic, okay? I see sine squared plus cos squared. That, my friends, is 1. So this actually gives me 2 plus 2 sine theta over cos theta times 1 plus sine theta. And look at where that gets you. Both of these are divisible by 2. So we could factor out a 2, and these will cancel, right? And what I'm left with there is 2 over cos, and that is exactly what's on this side. Okay, if you have other questions about those, I have about 50 videos from when I used to teach pre-calc of just doing more examples of those. So if you want them, just shoot me a reminder. I'll send them to you. All right, last one. I'm going to leave number 9 as a challenge for you, but let's look at number 8. Now, could you change this into sines? But then you're going to have like 1 over sine squared minus 1 over sine. It's going to be nasty. So what I see here is, let me say that this looks like a quadratic. Let's say let u equal cosecant. Then this would be u squared minus u minus 2 equals 0, right? And that's factorable. I can do that all day. This would be u minus 2 and u plus 1. So here's what I wind up with. I wind up with that u equals 2 or u equals negative 1. And so I know that cosecant is 2 or cosecant is negative 1. Remember, we're not done yet, because that means sine will be the reciprocal of that. Sine will be the reciprocal of that. Now, luckily for us on the negative 1, that is quadrantal. That one's pretty straightforward. This is just 3 pi over 2, because that's on the unit circle where the y value is 0. For this one, we need to think about what quadrant sine is positive in. That's here and here. My reference angle is pi over 6. And so this will be pi over 6 or 5 pi over 6. So we have 3 solutions there. All right. I'm going to hang out for about 1 more minute, but it looks like most of the people that were on have evacuated. So send me any questions. I'm going to hang out for a minute. I'm probably going to eat while I hang out. And then if you have other questions while you're studying, or if you're watching this later, just send them to me. I'm happy to answer questions anytime. All right, I'm wrapping it up. The last person has signed off. I will see you guys in school. Send me questions, and good luck studying.